All right, hello everybody. Today we're going to be talking about using the p-series test when checking for convergence at an endpoint. So first off, we got to address what is the p-series test? So the p-series test states that any series of the form 1 over n to the p, where p is a constant power, it's not going to change, and it's a constant number, will converge only if p is greater than 1. This form right here, we call it a p-series. That's why it's called the p-series test. And so now that we know what it does, we have to explain why it works. So if we go back to things we learned before, we learned about simple harmonic series. And we know that the simple harmonic series is the series of 1 over n. And we know that that series diverges. What we can also know now, knowing what a p-series is that we know the simple harmonic series is a p-series where p equals 1. So from this we can gather that whenever p is less than or equal to 1, the series will diverge. Now we've got to address what happens when p is greater than 1. We have to prove that it will converge whenever p is greater than 1. So we're going to do this using something else we learned previously, the integral test. So we know that the integral test says that for any series, if you take the integral of that series and the integral converges, that series will also converge. So that's what we're going to do for a p-series test, a p-series that's got a p of greater than 1. So what we've got set up here is the integral from 1 to infinity of 1 over x to the p, and we take the antiderivative of that right here, which gives us 1 over p minus 1. So since we know that the integral converges, the series does as well. And so everything we just said about the p-series in the what it says portion, we have now proved. So let's move on to an example problem. How can we actually use this when we're doing calculus problems? So what we're going to do is try to find the radius of convergence of a series. The series that I've thought up here is the series of 3x to the n over n squared. We're going to have to find the interval of convergence of that. So just like we learned before, step one to finding the interval of convergence is finding the endpoints of that interval of convergence, and that's going to be done using the ratio test. If you don't remember what the ratio test is, I'll go over a brief overview. So first we've got our series right here, and then we are going to initiate the ratio test, which is the limit as n approaches infinity of a to the n plus 1 over a to the n if the series is a to the n. And we can see that right here. Always remember your absolute value bars. They are very important at the end. And what we've got right here is 3x to the n plus 1 over n plus 1 squared, which is just a to the n plus 1 of this, and then the normal version. And we have some canceling out that's going on. And eventually, we will get it to this point right here. We've split it up into two different limits. We've simplified it a bit. If you want, you can pause the video here, just go over the steps of how we actually got here, but we're just gonna, for the sake of time, move on right now. So when we get here, we notice that this limit right here is going to amount to infinity over infinity, and then we're going to use L'Hopital's rule, like we learned before. We're going to take the limit of the derivative of the limit that was previously infinity over infinity. However, the second part of this, remember we split it up, is going to stay the same. And once again, even after doing L'Hopital's once, that same series is still going to be infinity over infinity, and we're going to do L'Hopital's again, and we're going to get the limit as n approaches infinity of 2 over 2, which is, as we know, 1. So now we have 1 over the limit as n approaches infinity of the absolute value of 3x. Now from the integral test, we know that if the limit equals a number L, if L is less than 1, the series will converge. So we have gathered that L is going to be the absolute value of 3x. So therefore, for this series to converge, the absolute value of 3x must be less than 1. So that's how we get the endpoints of our interval of convergence. We split it up into -1 is less than 3x is less than 1, which gives us our endpoints, -1/3 and 1/3. Now, let's move on to the second step. The second step is going to be checking for convergence at the endpoints themselves to see if the endpoints are included in the interval of convergence. And the way we're going to do that is by plugging them into the original series. So, as you can see here, we've got the original series here, 3x to the n over n squared, except x is -1/3, our first endpoint. So, we multiply that out, and what we get at the end here is a p-series where p is equal to 2. And by the p-series test, up here, we know that it will converge if and only if p is greater than 1. So, because p equals 2, we know that this series will converge absolutely by the p-series test. Because it converges absolutely, we don't have to use the alternating series test to check for conditional convergence. Now, for the next step, we're going to move on to checking the second endpoint for absolute absolute or conditional convergence. Once again, we're just going to plug that in right here. We have, instead of x, 1/3, which is our second endpoint. And once again, we get another p-series with p is equal to 2, and we come to the same conclusion that it converges absolutely by the p-series test. And our final step in the process is to state our interval of convergence. Because both of our endpoints converged absolutely, they will both be included in our interval, and our interval will be this right here. All right, hopefully that gave you a good idea of the p-series test and how it is used when trying to calculate convergence at endpoints. And I guess I'll see you for part 2. Thank you.